I'm going live. Yeah, we are live now.
Hello and welcome. Tonight we're going to have a talk from Emma about calculating pi on the Google Cloud Platform. I'll hand it over to Emma now.
Okay, cool. So I can just go ahead and present, maybe. So I hope you can see the screen. Hi, my name is Emma, and I'm a developer advocate at Google Cloud. This talk is about calculating pi on Google Cloud. My Twitter handle is YURYU, and thank you very much for having me today. I live in Seattle. There's a little bit of time difference between Seattle and Australia, but I'm very happy to be here today. So we calculated pi up to the 31.4 trillion digits after the decimal point, and that became a world record in 2009. And before explaining our particular record, I'd like to take a little bit look at the history of pi and computers. This is written in the Art of Computer Programming by Donald E. Knuth, and he says human progress in calculation has traditionally been measured by the number of decimal digits of pi. So we collectively, as humans, have calculated pi for actually thousands of years. And here's the table. Back in BC 2000, so this is 4,000 years ago, humans seem to know pi was close to 3.1. And in the 15th century, mathematician in India calculated pi to 10th digit. And since we got computers, like electronic computers, we began calculating thousands, millions, billions, and trillions of digits. And the blue records here are calculated by supercomputers, and the orange records or yellow records are calculated by desktop computer or PC server. So it's a regular single node computer. And our record in 2019 was calculated by cloud. And as you see here, our record, 31.4 trillion digits, is no longer a world record because someone calculated 50 trillion digits this year. So that's news. But as you see here, there is a fierce competition. And there are actually two forms of pi computation. One is to calculate all the digits from the first digit, like 3, to the last digit, but there is not actually a last digit. And the current world record is 50 trillion digits. And this is very memory intensive. You actually need to contain all the numbers. And the other form is to compute a small number of digits at n. And this is done in binary digits, not the decimal digits, but this is binary. And this scales very well. You don't have to store all the digits, and the current world record is 10 to the power 17th hexadecimal digit. And the second algorithm is actually used to verify the first algorithm. So instead of calculating everything twice, we use the second algorithm to verify the last about 100 digits to make sure our calculation is actually correct. Why is it difficult to calculate pi? Because in order to calculate trillions of digits, we need to store everything in memory, and it's very memory intensive. And the entire data set could be hundreds of terabytes. And currently, we don't have computers with hundreds of terabytes of DRAM, so we need to store data in the disk or store on other nodes across the network. And unfortunately, disks and network are not as fast as processors, so that communication is actually the bottleneck, and the computational power doesn't really matter anymore. And why is computing many digits so memory intensive? Because as you have more digits, so here we have the computational order complexity here. For the time complexity, it's all log n to the power of 3, and for the space, so memory requirement is all n times log n to the power of 2, where n is the number of digits. So as you see here, the memory requirement, space requirement actually grows super linear. So in order to calculate twice more digits, you need to have more than twice as memory. Then why don't we just use supercomputers, because they are super, right? And yes, we could, and in fact, we have used various supercomputers in the past to calculate these digits, and these notable records are all achieved by using some of the fastest supercomputers in the world. But at the same time, it is increasingly difficult to write a program that runs on a supercomputer, because these computers have become much more parallel. Sorry. For example, the current world's fastest supercomputer is Fugaku, and it has more than 7 million CPU cores and 158,000 nodes. So when you write a program, it actually needs to scale across millions of cores, and it's very difficult to write a program that scales on millions of cores. So we decided to use cloud, and in fact, several of the past records used single node computers. We calculated 31.4 trillion digits, but the exact number of digits is 31415, etc. So this is the first 14 digits for pi. And we spent 121 days. And we run a program called yCruncher. This is something you can download from the internet and run it on your desktop or laptop. So one of the benefits here is you can actually use an existing software instead of building something from scratch. And the main compute node is the 96 vCPU instance with 1.4 terabytes of RAM. This is quite big, but not as big as some of the supercomputers or custom-made hardware. And there are a couple of interesting metrics, but one of the most interesting one is the total I/O. So over the 121 days, we read 9 petabytes of data and 8 petabytes of wrote 8 petabytes of data, and we need to make sure that every bit is correct, because this is a mathematical calculation. We can't afford to have a bit flip. So this proves that cloud is indeed reliable. And if you actually paid for the system as an external customer, you'd pay about $200,000. And this is quite expensive, and I wouldn't probably be able to afford that much. But the important thing is, I'll explain the details later, but if you repeated the same calculation today, you'd probably pay less than $30,000, US dollars actually. This is still a significant amount of money, but this shows how fast these cloud platforms actually improve over time. And this is also the first world record with a SSD drive instead of hard drives, and using the Intel AVX 512 instruction set. Why would you use cloud? Again, it's easier to run programs. You can just run off-the-shelf program. You don't have to build everything from scratch for massive power supercomputers. And it takes only a few minutes to start a new cluster. You just need to click on the web console, and you have a functioning PC cluster. And it's more reliable than a desktop computer or a server machine in your office rack or home rack if you happen to have a rack in your home, because cooling, power, everything is redundant, and even if there is a hardware failure, we actually live migrate when we can. So the average mean time to recover, so the time to recover from a failure is shorter than a physical hardware, because you just need to spin up another instance. And mean time between failures is also shorter than physical hardware, because we can live migrate between computers. And in terms of operations, it's just easier to run everything on cloud, because you can manage everything remotely. You can just use the web console or command line interface. And also, for example, when taking backups, you just need to create snapshots instead of copying everything from one drive to another. And here's the timeline. We started the discussion a year before the Pi Day in 2018. So after the Pi Day in 2018, we started discussion, and it actually took a while before starting the calculation, because this was mostly my 20% project. So this was not my main job, and it went smoothly. But we encountered a possible silent I/O error. So Y Cruncher has a mechanism to detect any, about 90% of memory or I/O errors, and Y Cruncher just detected one error in December, and we don't know the exact reason, but potential reasons it could include I/O errors, memory bit flip, or CPU error or something. And because we have backups, we were able to restart from one of the snapshots, and we finished the hexadecimal numbers calculation in January. And as I said, there is the independent algorithm to verify the numbers. So that number was provided by someone else independently in December. So I verified the numbers in January, and And then we converted the hexadecimal digits to decimal digits, and everything was complete in January. And we waited until Pi Day to make the announcement. This is the overview of cluster. So as I said, the main compute node has 96 vCPUs with 1.4 terabytes RAM, and it had 30 terabytes of SSDs to store the result. And in addition to the main node, we had 24 storage nodes to store the temporary work area. And these are just regular Linux systems instead of Windows system, because we had to use separate network nodes because you can only this has changed, but you could only mount up to 64 terabytes, and we need about 240 terabytes of disks. For the main node, there are a couple of options, but we had to choose the fastest computing instance. And at the time of the calculation, we had these options: N1 MegaMem 96 and N1 UltraMem 160. And N1 MegaMem 96 is the one we decided to use. This has 1.4 terabytes of RAM. And N1 UltraMem 160 has 160 vCPUs. And this is a 4-socket Broadwell system. And this has more memory with 4 terabytes. And it looks like N1 UltraMem 160 is actually faster than N1 MegaMem 96. And it is for certain workloads. But we decided to use N1 MegaMem 96 because Skylake is a newer CPU than Broadwell, and it supports AVX512. That means we could actually compensate the fewer number of cores. And Y-Cruncher is not particularly optimized for many sockets. If you have 2 or 4 sockets, memory is attached to each of the sockets, so there's actually communication overhead between different sockets. And Y-Cruncher doesn't particularly handle that situation well, so actually having fewer sockets with faster CPUs was faster for this particular workload. And for the storage, as I said, one compute engine can mount up to 64 terabytes of persistent disks. This was expanded after we finished the calculation, but this was the limitation at the time. And so we had to mount something on top of the operating system. So instead of using the cloud feature, we had to use the network protocol, ISCSI, to mount the disks. And we also decided to use SSDs instead of hard drives because nobody had tried SSDs before, and people kind of thought, okay, SSDs are not ready for these write-heavy workloads. And we kind of wanted to show that SSDs were indeed capable of handling petabytes of writes. And in order to combine 24 disk nodes, we use Y-Cruncher's RAID layer instead of using the operating system RAID layer, because this is optimized for Y-Cruncher, and it's faster than using Windows RAID system. And then another benefit is we would have 24 different NTFS volumes. So when taking backups, you don't need to worry about synchronization issues. So you don't have to keep the metadata consistent across volumes. So that's another benefit. And we chose number 24 after running some benchmarks, and 24, 24, 20, 24, 32 nodes, and 24 seem to perform the best with 26 gigabps read throughput and 16 gigabps write throughput. And because the network cap was 16 gigabps for egress at that time, so it was actually hitting the network cap. And there are a few optimizations and techniques we use, but most importantly, we had to take backups because we expected that our calculation would take probably 5 to 6 months. And Y-Cruncher has a checkpoint feature, so it saves internal states asynchronously. And we would need to copy the checkpoint files. But because Y-Cruncher used to, so this has changed because of our feedback, but Y-Cruncher actually rewrites the entire checkpoint file. So we need to make sure that we take backups outside of these checkpoint windows. Otherwise, the status would be inconsistent. So what we did was actually looking at the task manager and made sure that Y-Cruncher was not actually writing to the disks. And we use persistent snapshots to store the checkpoint files. And in order to automate the process, we wrote scripts to take backups and restore, and run the script manually once or twice a week. And if you haven't restored from backups, you probably don't have backups. So you actually need to test that you can restore from backups. And we practice some possible scenarios like stop the program or shut down the Windows instance and made sure that we could actually restore from the backups. And if you haven't used persistent snapshots, this is really cool. When you take snapshots, multiple snapshots of the same disks, these would be automatically compressed as incremental backups. So we have 5 snapshots here, and the first these are all for 10 terabyte disks, but the first 2 snapshots are 1.8 terabytes, but the last 2 snapshots are just 2.6 or 2 megabytes, around 2 megabytes, because we didn't write data after January 18th. So when you have a lot of disks and continuously take backups, persistent snapshots actually store data as incremental backups instead of storing entire disks multiple times. And it's actually very fast to take backups. We had 240 terabytes of disks, and they were not full, but usually it took about 10 to 15 minutes depending on the load, but to copy the entire 240 terabyte cluster. And it's cheaper than persistent disks, obviously. Another technique or important factor was monitoring, because you need to run the program for multiple months, and you probably don't want to look at the task manager or top command 24/7. We set up both Stackdriver and Datadog to kind of experiment with both systems. And I also wanted to learn about both of these. And I ended up using Datadog in order to share this dashboard to Alexander A., the Y-Cruncher developer, and my managers. And so as you can see here, you have this progress number, uptime, and CPU usage, disk usage. So just looking at this dashboard, you could tell whether the system is running or is stuck, or Y-Cruncher is doing I/O or a CPU. heavy operations, etc. And most importantly, the progress. And we had two alerts. One is for individual host downs. So if one of the hosts, including the storage nodes and the CPU nodes, went down, you'd receive an email. And the other alert is for the average CPU usage for the compute node. And if that's less than 1% for over the 1 hour window, you'd get an email. And we set the window to 1 hour. This is relatively long. If you are running a web application, probably you don't want to wait for 1 hour to catch abnormality. But this was a long-running process, and actually waiting for 1 hour to make sure that I wouldn't get any false positives, because as you see here, the CPU usage fluctuate quite a bit. So sometimes it's near zero, and sometimes it's close to 100%. So it's kind of difficult to set reasonable percentage for example, 1 minute or 5 minute windows. And this 1 hour window actually worked really well, so I didn't really receive false positives. What we've learned, in hindsight, this might seem like a simple task of running the program for 4 months. We already had the program, and we already had the cloud. So I just used the web console to launch a couple machines and run the program on Windows, and anyone can do that, right? But before we began, we didn't know that we could actually break the world record with cloud. And even some of my colleagues were kind of skeptical of the idea. And we were not quite sure what would happen if we wrote petabytes of data from a single virtual machine. And we were not quite sure that iSCSI was the right option to handle such intense IOs. And now we know it's possible, and this architecture actually works for this particular workload. And the good thing is with the cloud is anyone can replicate the architecture. So if you know the reference architecture, you can copy it and run your own application now. And because we know that we can run long-running processes in cloud. And what we got today, so this was started in 2018, and this is 2020, so quite a few things have changed. We've improved the cloud. We have new virtual machine types. We have increased network bandwidth, more storage per virtual machines, and we also increased the storage bandwidth. So let's take a look. We have bigger and faster machines. So we use N1 MegaMem 96, but we have N2, N2D, and M2 instance types. I know these symbols, like these names are kind of confusing, but if you have N, that's a general purpose machine. If you have M, that's a memory optimized machine. So if you want to have a lot of memory, you'd need to use M. And if you just use a regular, if you have general purpose regular workload, that's N. And N2 is 20% faster per price over N1. And we also have N2D, which is a AMD-based machine with up to 224 vCPUs. So this has quite a lot of cores. And M2 has up to 12 terabytes of RAM. So if you actually need a lot of RAM, you also have this option. And you can also mount up to 257 terabytes of persistent disk to one node. So instead of, you wouldn't need 24 different disk nodes to store 240 terabytes of RAM. And the network bandwidth was increased from 16 gigabits per second to 32 gigabits per second. So you can send data twice as fast today. And storage got faster too. We have standard persistent disk, SSD persistent disk, and local NVMe SSDs. And persistent disks are persistent, so these are network drives. But when you hear network drives, you might think network drives are slower than local drives, but that's not really the case. For standard PDs, so this is hard drive based, you can read at 1.2 terabytes per second and write at 400 megabytes per second. So this is actually much faster than a single hard drive. And for SSDs, the IOPS, IO operations per second is up to 100,000 per VM. And if you do a DIY PC work, 100,000 is actually close to the SATA limitation. So this is as fast as a SATA drive, and then again the throughput is faster than a local SATA drive. And if you absolutely need a fast local drive, you have the local NVMe SSD, and the IOPS is up to 2.4 million for reads and 1.2 million for writes. This is quite fast, and the throughput is 9.3 gigabytes per second for reads and 4.6 gigabytes per second for writes, which are also fast. Of course, you probably don't need this much throughput all the time, but having this option is great. And so we use SSDs, but instead of using SSDs, we could use standard PDs and achieve the same throughput today. So with these bigger, faster machines and faster network and disks, the 2018 architecture can be changed to save money on storage and machines, and actually finish the calculation much faster. So we haven't tried, but we kind of estimate the total cost would be around $30,000 today. And again, with cloud, you don't need to buy new hardware. You just need to change the configuration and reboot the machine, and you get the fast new machines. And for the storage and network, you even don't need to change the configurations. You automatically get the faster network throughput and storage throughput. And last part is, why did I decide to calculate pi in the first place? Like, because you don't do that often, right? I was obsessed with pi for a long time. I was born and grew up in Osaka, Japan, and it's the third biggest city in Japan, but we didn't calculate pi like any other cities in the world in our daily life. I started programming when I was 11 years old, and one of the first programs I wrote was actually a program to calculate pi, and this is my code from 1997. And because this just used double precision floating point variables, it was only able to calculate up to about 20 digits. And then the world record was 60 billion digits, so that's the gap I had between a world record holder and middle school kid. And I wasn't particularly good at math, so I just my high school teacher suggested I study liberal arts. So in Japan, you actually choose STEM or non-STEM in high school, and my high school teacher suggested non-STEM courses. So I decided to study education and psychology in college, partly because the entrance exam had only English and geography, and I was good at both. Partly because psychologists seemed really cool, and I wanted to build an AI, and learning about human psychology could help with like playing with AI, I thought. And then after started to study in college, my professor came to me and said, "Hey, if you like computers, you can change your major." And so I did. I switched to the computer science major in the second year, and eventually finished a master's course in computer science. And this switch was, I still think, one of my favorite, best decisions in life ever. Not necessarily because you need to study computer science to become a good software engineer, but because I changed from something I was told to do to something I really wanted to do, and I don't regret at all. And then I started my career as a software engineer after graduating from the university. I first did an embedded programming work at Panasonic, and then after 2 years and little, I changed my job to what we call today as site reliability engineering. So I moved out of embedded programming into the world of server management. And then I kind of wanted to work at Google, but I didn't pass the interviews. A friend of mine sent a referral for me, and then I took the interviews, didn't get an offer 4 times before finally getting the offer. And then I had different jobs over the course of 5 years. So as my 5th job, I joined Google as a customer solutions engineer. And then I moved from, so this is a position is in ads. And then I moved out of ads to cloud. And after joining DevRel, I didn't think I would calculate pi as a developer advocate, but the team had a tradition of Pi Day celebrations. And in 2018, a colleague of mine calculated 1 trillion digits using one of the memory optimized instances. And then I realized during the planning for the next year, cloud might be able to break the world record. So this is the guesstimate. We had the numbers for the previous world record, 22 trillion digits, and the total I/O for 22 trillion digits was 15 petabytes. And we knew the numbers for cloud. We knew the disk throughput, and probably for 31 trillion digits, the total I/O would be around 20 petabytes. So it'll probably finish in 5 to 6 months, and it actually finished earlier than 5 months because of some optimizations under the hood, and the read throughput is faster than 16 gigabits per second. And I proposed this idea to my managers, my manager and director, and they said, "Okay, sure, give it a try." So I did. So this is a combination of something I had wanted to do, and suddenly I had all the resources and team support, and then but I didn't do the calculation for 1 year, and then I had that switch. A colleague did the previous Pi Day celebration, so I began to think about breaking the world record. And I had never thought I'd become a professional software engineer until I became one. My high school teacher told me it's hard to do a software engineering job, and I wasn't great at math, so why would I become one, right? And even after started working, I didn't think I was a good software engineer. And when I was in school, I thought, okay, I might be good in the classroom, but because I'm not a professional, um, professional software engineers are better than this. So, but that's not the case, you know. And even after started working, I didn't think I was that good, despite all the evidence that I was good enough. And I didn't think I would break the world record of pi, and I didn't think that world record would become such huge news. We had quite a lot of coverage from all the news media around the world, including the BBC, CNN, NPR, which is the American radio station, NHK, Japanese broadcaster. Hundreds of articles came out, and this was because when we finished the calculation, my director said, "Oh, we can go big." I was like, "I'm wondering if I should have just a personal blog, or do you think the Google blog team might be interested in publishing something about this world record?" And my director was like, well, I'll talk to the marketing director, and we can go bigger. So the Google marketing and PR team worked really to put everything together. So we had that big announcement and news coverage. So this is the last slide, but combination tools. So we already had all the necessary tools, and all Googlers actually had access to everything, right? But nobody actually tried. So actually combining tools is a creative job, creative work, and you can solve a new problem by just choosing the right tools and give it a try. And I was lucky, I was fortunate that I had access to the resources and the manager support and team support. But I was ready. I knew how to use cloud, and I knew how to calculate pi. And also, cloud is a new tool for large-scale computing. You can just try different ideas, different configurations. You can run lots and lots of experiments in a really high speed. And we used to use supercomputers, and I couldn't afford a supercomputer. I still don't, but without actually buying one, my childhood dream came true. So I was a world record holder for 1 year. That's my talk. Thank you very much. Do we take questions or comments?
Thanks, Emma. That was quite an interesting talk. I've got a couple of questions for you, though. Just out of interest, how many attempts did it take you in setting it up before you actually ran the calculation?
How many times did I set up?
Like you, yeah, when you're setting up the environments and stuff like that, how many times did you attempt or do different setup combinations before you ended up doing the final calculation?
So Y-Cruncher has a small benchmark program to measure the disk performance, and we tried iSCSI, different file systems, and different number of disk nodes. So roughly 10 to 15 times. So we run the program. We run the benchmark. Yeah, but 15 to 20 times, and Y-Cruncher has some optimization parameters. So that's what I did, and because the reason it took 6 months before actually starting calculation was partly because we had our main jobs, and that timing was we had to start the calculation really in September to finish the calculation before the next Pi Day. So that was our estimate.
Did you give GCP a heads up before you done all the calculations?
No. So 240 terabytes was not necessarily. So of course we had to request additional quarters, but 24 nodes or 240 terabytes of storage is not something you actually need to talk the SRE to or the capacity planning team to get access to. So no, that's part of the standard quarter request process.
I was just curious as due to the fact that you're hitting the 16 gigabytes throughput. Is that
16?
You're saying you're hitting the 16 gigabytes throughput on the I/O for the network, I think it was.
16 for
gigabits a second.
Oh yeah, so that's the network egress cap. So per virtual machine, you have you have unlimited bandwidth for downloads, but you have a limited bandwidth for uploads, and that's not necessarily about the individual virtual machine, but how can I say? So that's not necessarily set because of the hardware limitation. It's there to protect all the different users sharing the same infrastructure, and we were able to increase the bandwidth from 16 gigabits per second to 32 gigabits per second last year. I think last year or this year. Sorry, I don't remember exactly, but we did. But it's a cap, so you can't go higher, but you don't break anything by just trying to get higher.
Do you think that you would attempt again in the future?
Yes. So we have. Do I want to break another record?
That's the question, isn't it?
So we have the 50 trillion digit record, and obviously I can't talk about future GCP features, but we plan to continue improving the infrastructure, and if we have significant increase in the areas that I touched in this presentation, maybe I can try something like 100 trillion digits with Google Cloud, so there are a couple of factors. Even with the current infrastructure, you can spend like 1 year to crunch the numbers. If you can keep running the software for 1 year, obviously you can calculate more digits. But unfortunately, with the current computers, with all the hardware, even with ECC memory or network checksum, CPU, error checking, you don't have 100% reliability. You have, even with ECC, you have probabilistically you have a memory flip, or for disks, for cloud, it's error coded, so you probably don't have data corruption. But for memory and processors, there is non-zero chance of getting a bit flip over the course of a year if you have hundreds of terabytes of data. So with the current hardware, any hardware you can get running Intel CPUs, 6 months is a safe upper limit for the duration. And if you run a program for more than 6 months, chances are there is a non-zero chance of spending 1 year running the software and the servers and get the wrong result. So we actually need faster network and faster infrastructure to break like 100 trillion digits, and that's something I'm waiting for. So yeah, if the conditions are met, I definitely want to try.
Sounds like you got your future planned out for you.
Yeah.
Is it fair to say that you can recite pi to quite a high number now?
Can you say again? Sorry.
Is it fair to say that you can you've learned to recite pi to a high number now, like number of digits
Number of digits.
of pi? Sorry, like just from a mental point of view, have you learned to recite the pi to, the digits of pi to quite a high number, or is it
No.
no?
So
Because I'm yeah, 4 digits is pretty much my limit that I've ever got to, or 4 or 5.
At one point in my life, I was able to recite up to 20 digits, and that shrunk down to like 7 now. So no.
Fair enough. Anyway, I think that's pretty much us for the night. Unless there's any other questions. I think we will probably call that. Thank you for your talk, and hope to hear from you again another time.
Thank you. And yeah, I can be reached on Twitter or my work email address. It's the same as my Twitter handle. So if you have any other questions, comments, feedback, I'd be happy to hear from you at YU on Twitter or YU at google.com. I hope you enjoyed the talk. I hope you enjoyed the talk.
Yeah, it was very good. Thanks.
Thank you.